That's your report. This incident report. 6D1 32.
16.
6D1 32.
61
And
24.
Also 24.
So 24 or 5.
Don't. Where's my number?
30.
60, 32.
Yeah.
Yes.
24.
24.
How can you remember that?
And also I think
Just copy the formula and change.
well, Janet,
After.
not on here, right?
24.
24 is Janet.
Yeah.
So only two students answer.
Yeah.
But how many girls are?
Wait, really?
14. Yes.
Hi.
Okay, yeah, so that's all. Okay, and I hope that you have brought this paper from last time. Oh, you were not here last time.
No, he was.
Oh, you have.
Yes.
Yes. Okay, yeah, so you may want to take it out because later our decision will be based on that. And after we finish all the organic reactions, hopefully we'll be able to wrap up this chapter.
Not yet finished.
A little bit behind schedule, alright?
Not a little bit.
Yeah, actually, quite important. Behind. So let's start with.
Oh my god.
Well, yesterday we stopped here on the reduction of the aldehyde and ketone. Okay, so like today we will pick up from the carboxylic acid part. Okay, and then we will look at the various reactions of carboxylic acid. So let's put this in here. Sorry, testing. Yeah, so the reactions of carboxylic acids. Okay, remember carboxylic acids, they have this general formula CnH2n plus 1 COOH. Or simply we'll write this as RCOOH because this is what the R group is. Okay, so you have an R here and you have COOH. So know what to call these two groups. This group on the left, we call this the LQ group. N can be any number starting from 1, okay? Or yeah, it can even be 0 here for carboxylic acid. So LQ group. For carboxylic acid, R starts from 0. N starts from 0. Because what's the simplest carboxylic acid that you can think of? What is the simplest formula of carboxylic acid that you can think of? Is it CH3COH? Can we do something simpler? It's HCOOH. So put this down. This is why I wrote N greater than or equal to 0. When N is 0, you will end up getting this formula HCOOH. Yeah, many students think that N must start from 1. This is not true in this case, okay? And I would like to take this opportunity to do this very quick recap with all of you. So for alkane, what's the general formula? CnH2n plus 2. Okay, yeah, maybe take some more after lunch. Okay, we have alkene, which has general formula H2n. For alcohol, we are talking about alcohol, not that. So mono alcohol. We don't mean the diol or stuff. The general formula will be CnH2n plus 1 OH. And finally, here we have carboxylic acid, which you just saw. Okay, they have general formula CnH2n plus 1 COOH. So these groups that I'm highlighting now, they are called the functional group. Okay, so they are the functional group. For carboxylic acid, the functional group, we call this the carboxyl group. So the functional group is this part. We call this carboxyl group. And for alcohol, the functional group is called the hydroxyl group. Okay, note the difference between drawing the functional group and naming the functional group. When they ask you to name the functional group and when you put OH, you're not answering the question. Okay, when they ask you to name it and you write this down, that's not answer to the question. It should be hydroxyl. Okay, so write down hydroxyl group. For alkenes, the functional group is kind of hidden as you cannot see in the formula. But what is the functional group of alkene? What is the functional group of alkene?
Double bond.
CC double bond. Yeah, don't just put CC double bond. Don't just put double bond in the answer. Write CC double bond, or you can draw it. Okay, like that. That's the functional group of alkene. For alkane, they have no functional group. Okay. And what other things do I want you to put down is the starting number of n for each of these homologous series. So we have for alkane, what's the smallest number you can assign to n? 1. Yes, n starts from 1. Can you put down n is greater than or equal to 1? Yeah, n cannot start from 0 because you must at least have 1 carbon. So the simplest alkane will be CH4, and then the second one, let's just put 2 for each of these, C2H6. For alkene, what's the smallest number you can assign to n? 2. Why not 1?
If not, no C for double bond.
Yes, okay. Yeah, so you may know this now, but later in the exam, sometimes you may just forget. So I need to just remind you all to pay attention to the starting number of n. It may not always be 1, okay? And in here, you have C2H4 and C3H6. What about alcohol? What is the lowest number you can assign to n? 1. Yes, so n is greater than or equal to 1. So can you name these two alcohol for me? Just want to integrate.
CH3OH.
Yes, that's the formula. What about the name?
Methanoic.
Another acid is the suffix.
Methanol.
Methanol. And the second one will be
Oh, right.
ethanol. No, yeah. Yeah, maybe put this down as well. Okay, the suffix. So the suffix for alkane must be ane. The suffix for alkene must be ene. The suffix for alcohol must be anol. And finally, what is the suffix for carboxylic acid? Anoic acid. Okay, yes. I know it's very easy to confuse these two functional groups. It all comes down to whether they have a CO double bond or no. So, what is the lowest number you can assign to n for carboxylic acid? 0. Okay. Yeah, so you can have n equals 0. What do you call these two carboxylic acid? When n is 0, what is the name of this carboxylic acid?
Don't know.
What is the root for 1 carbon?
Meth.
Phenolic acid. Okay, yeah, so remember this.
What about the 01? How do you call the 01?
Oh, this is methanol acid as it has 1 carbon.
Oh.
Yeah, this already has 2 carbons, you see.
Oh, okay.
Yeah, a very common mistake students make is they only count the number of carbons in here. You know, this may not be the only source of carbon. There's also carbon in here. So you have 1 carbon, therefore meth, phenol acid. Then you have 2 carbon, therefore ETH. I want to use these 2 examples to show you that n, the number n, may not always be what you look at when you determine the root. You have to also count the C in the function group. So don't make this careless mistake. A lot of students incorrectly assume that n is the number you look at when you determine the root. I wish it was that simple. Because some function group itself has C in it, right? Yeah, so don't make mistake. So we write that down. Don't determine the root. So the root meaning something like math, F, or build, etc. I'll just put 2. Just by looking at n, okay? Just by looking at n, as it may be misleading for certain chemicals, for example, carboxylic acid. Just by looking at n, you see here these numbers don't match. Just look at 0. 0 and 1, they are not the same number, you see, okay? So if you wrongly assume that n must be equal to the number of carbon, you're wrong. Okay? Right. Now, back to what we were discussing, okay, moments ago. The carboxylic acid, okay? So this group remember the blue group, okay, the one I highlighted in blue is the carboxyl group. And we have a few reactions of carboxyl acid. Let me draw this flow chart. You have RCOOH. They can react with they can react with the alcohol, so they can react with alcohol to form ester. Okay, so to form ester. And they can react with, so you see here, they can react with ammonia to form like what we call the amide. Yeah, and these reactions, okay, going to the right, we call these condensation reaction. So these are condensation. So condensation means the joining of two molecules to form, water as the other product. Okay, so these are condensation reactions. So we will look at them now. Okay, let's take a look at the first one, the formation of ester. So we already, I know we stopped at the preparation of ester yesterday, but this time we will also look at the reaction going in reverse. Okay, so ester, the connection to carboxylic acid. First, can you put down this equation from yesterday, RCOOH? When you react it with ROH, I just want you to draw your attention to the reversible nature of this reaction. So I'll ask you which of these reactions are reversible, which of these are irreversible later. So at first, you can put down this reaction is reversible. So the requirement for this reaction is the use of which catalyst from yesterday? What is the catalyst for esterification? Concentrated sulfuric acid. It doubles not just as a catalyst, but also as a dehydrating agent, right, from yesterday. Okay, so write down con H2SO4. So for catalysts, you don't write it as a reaction or product because they are not consumed nor are they formed. They are instead written above or below the reaction arrow. Okay, so it's not up to you where to put it. You have to put it below or on top of the arrow. And then on the right, we have ester, and please don't confuse ester with carboxylic acid. I know they look very similar, right? Don't you think? Okay, they both have COO. But esters, this is the functional group of ester. We call this the ester bond. Yeah, for those of you doing biology, you may recognize this in triglyceride, in fat. Okay, so fat is an ester. It's a triester, okay, because there's 3 ester bond. And then you have this functional group, the carboxyl group, okay, for alcohol. So write down this is carboxyl, COOH is carboxyl, therefore this is a carboxyl acid. This is hydroxyl, so this is an alcohol. This is not carboxyl or hydroxyl, but we call it an ester bond. Yeah, so ester is COO, hydroxyl is OH, carboxyl is COOH. Note that I wrote another dash in here. Yeah, that's because the COO has to connect to something on both sides. But the hydroxyl and the carboxyl has to only connect to things on one side. Okay, yeah, be very careful when you write this. This has 1 dash each. This has 2 dashes each, as it connects to 2 things on the 2 sides, and this has to only connect to 1 thing. That's some time into detail. And finally, we have, of course, water. Okay, yeah, so if you don't like writing H2O like that, just write H2O. That's the esterification. Yeah. Okay. Now the next thing we look at is amide. So what are amide? So there are 2 types of amides. Okay, they are called unsubstituted amide and N-substituted amide. So 2 types of amide. So first of all, amide all have CON. Okay, all amides have the following functional group: C double bond O N. I like to remember this as con. I mean CON, right? So when you put the letters together, you have con. Okay, so CON. Look for these when you are searching for an amide. But then there are 2 types of amide. Depends on what gets connected to the con group. Okay, you can have R, C double bond O, and HH. We call this an unsubstituted amide. Yeah, unsubstituted, because on these two groups, there are no alkyl groups, okay? So when you substitute the hydrogen with an alkyl group, we call them substituted amide. But because these are not alkyl groups, these are just hydrogen, we call them unsubstituted amide. Because these, none of these are, so none of these are, is or are alkyl groups. And by these, I mean these, okay, these two. And then we have an N-substituted amide. So N-substituted amide will be those with at least one alkyl group on the end. Okay, so you have two possibilities here. You can either have two alkyl groups or just one alkyl group. Yeah, the alkyl group may or may not be the same. Doesn't matter. Okay, so yeah, we have two types of amides. On the left, we have the unsubstituted amide, this one. And on the right, we have what we call the N-substituted amide. Because the N has one or more hydrogen substituted. Okay, so-called because at least one H on the N, okay, on the N has been substituted with an alkyl group. Yeah, so with alkyl group. So R, okay, so we have the R here. So this is an R, this is, these are the two R's. So you have alkyl, alkyl, alkyl. So in exam, they will really just ask you to identify which type of amide it is. Okay, so to check that you understand what I'm saying, okay, yeah, so there are two types of amide.
Sorry, can you zoom?
Yes.
So-called.
So you have unsubstituted amide, where next to the con, yeah, you may want to highlight, pick out a highlighter. Help me highlight the con group first. This is the con. Whenever you see con, it must be an amide. But which type of amide it is? Is it unsubstituted or N-substituted? You look at the N. Just like you will look at the carbon bonded to OH when you decide a class of alcohol, right? Like primary, secondary, and tertiary. Here, you look at the N. You find out how many alkyl group is attached to this N. Okay, so here, there are none. So unsubstituted. And if you see any alkyl group, whether it is one or two, doesn't matter. If you see an alkyl group in here, it is N-substituted amide. And you don't have to name them. The good news is, however, you need to know which is unsubstituted, which is substituted. Okay? So, to see if you can identify them, help me write down or copy these skeletal formula, and you decide whether they are substituted or unsubstituted. So you have this, and you have this, and then finally you have this one. Yeah, so what do you think is the nature of these three amides? No need to name them. Yeah, only unsubstituted amide do you need to name. Okay, they end in the suffix anamide. Okay, so anamide. So this is, how many carbons does it have?
3.
3. What is the root for 3 carbon?
Oh.
Pro, so propanamide base. So write down propanamide. Okay, so no need to name the N-substituted amide, not in DSE. Okay, so no need to name N-substituted amides. Only unsubstituted amide will be named. But still, I want you to check the number of alkyl group in here. Can you highlight the con group for me? Where is the con group in here? This one. Oops, wrong color. So you have the con group in here. Focus on the N. Is it unsubstituted or N-substituted?
Unsubstituted.
Unsubstituted. Because next to the N, what are they? They are H's. Okay, they are H's. So this is unsubstituted. Find the con with the second example. Is this N-substituted or unsubstituted? N-substituted, because there's an alkyl group here. This is the carbon, CH3. Okay, this is the CH3 group. So maybe you can use one additional color here. If you see any alkyl group, so this is an alkyl group. Yeah, Al being CH3 in this case. This is N-substituted. So what about for the last and bottom example?
Also in substitution.
Also n substitution. Okay, so now you know what n and unsubstituted alkyl group mean. What are the two alkyl groups in the last example? They are respectively
CH3.
and
C2H5.
C2H5. Okay, make sure you put a dash there to indicate that they are connected to something else.
Ethyl.
So this is the C2H5 group. Yeah, so put down, this is type 1, so this one here is type 1, and these two here are type 2. Yeah, so the N substituted amide. So why do we care which type of amide like an amide is? Okay, that's because the way we prepare would be slightly different, you see. So on the next page, we look at the preparation of amide. So any question on this part first? No. Okay, so we have two routes for making an amide. So two ways to make an amide. But there's only one way to make an ester, at least in this level. Okay, so two ways to make amide. The first way is to go from RCOOH to RCOCl first, and then to RCONH2. Right, so draw out the general formula. I mean, draw the full structure formula, or else it will be very hard for us to see what is happening. So this is RC double bond O OH. This is RC double bond O Cl. And then finally we have RC double bond O and H2. Yeah, you can almost see at a glance that the R group remains unchanged. Well, this means the R group is not the thing that is reacting, but it's the other part of the molecule that is reacting. It keeps changing its shape, okay, and its functional group. So let's see how this is done. Write down method 1 on the side first. So this is method 1. And what are the reagents required? The first reagent needed is PCl3. Does it ring a bell? We use this in the halogenation reaction of alcohol. Okay, this is the same thing we use to turn alcohol into chloroalkane. So we use the same thing to turn alcohol into chloroalkane. Now we will use the same thing here. Search for the pattern. You see, when you turn the OH group into Cl, you can also turn the COOH group, the OH part, into Cl. And the Cl comes from the Cl of PCl3. Okay, this is a halogenating agent. So this is to highlight the fact that PCl3 is a chlorinating agent. It has the ability to swap OH group for Cl. Okay? Yeah, and it can do this to both alcohol and carboxylic acid. It doesn't differentiate between alcohol and carboxylic acid. As long as it sees an OH, whether it is an actual OH of an alcohol or just a OH part of the carboxyl group, it will swap it for Cl. So it is, as such, a chlorinating agent. It has the ability to swap groups for Cl. Then, we have another reaction here. This requires the reaction with ammonia. So we'll write the equation for these two steps now. So write down step 1, and this is step 2. So step 1 looks like this. You have RCOOH plus PCl3 becomes RCOCl plus H3PO3. So this is phosphorus acid, not phosphoric acid. And to balance the equation, how many RCOH do I need?
1.
How many H do you have on the right?
3.
So that means
3.
3, yes, okay. So yeah, you can look for the H's. You can see that there are 3 H's and there are 3 O's. Yeah, so that means there must be 3, okay, of these RCOH on the left. That's step 1. Okay, pretty straightforward. Step 2 is where you react the RCOCl with ammonia. So So that's ammonia. And you have RCONH2 plus HCl. How do I remember this? Okay, maybe you're thinking. So maybe you can draw this out. You have NH2H. I like to sometimes look at NH3 as NH2H. Okay? So RCOCl, when it reacts with this, they basically swap place. The H and the Cl, they combine, and they become this. The RC double bond O and the NH2, they combine, and they form this. Okay? Yeah, that way you can rely less on your brain cells and because you're trying to understand the reaction, okay, how the products are formed. Okay? Do you see how this get to reassemble into the product? Right, and this is our amide. Is this N-substituted or unsubstituted?
Unsubstituted.
Unsubstituted. Okay, unsubstituted. So that's method 1. We have another method here. Only 2 methods, okay? Yeah, maybe that's giving you a nightmare. Okay, so we have method 2 below. So method 2 involves reacting the RCOOH with ammonia directly. Okay, so this will form RCOO. I'll ask you to write this equation because you should know. When I react ethanol acid, you learned this in acid and base chapter. When I react ammonia with carboxylic acid, okay, let's do a warm up first. Okay, yeah, because it's quite distant memory, right? When you react NH3 with HCl, what are the products? What is the product? What is the salt? Name it. Ammonium chloride. Okay, excellent. Yeah, NH4Cl. You can say the NH3 and the H, they combine to form NH4 plus, and that combines with the Cl. Now let's take things up a notch. So you have the NH3 and the H combining to form NH4. Now you have NH3 and H combined to form NH4 again. But what will be the other part this time? See? So this will be NH4 plus CH3 COO minus, right? What do you call this? If the top salt, you call it ammonium chloride, you will call this?
Ammonium.
What is CH3COOH, the acid called? Ethanoic acid. So this will be called ethanoate. Ammonium ethanoate, yes.
What?
Ammonium ethanoate. Right. Yeah, I know. Long time ago you learned this in SFX. Okay. But now we'll be using the second reaction here. Okay. So can you write this down? We sometimes write this as CH3COO minus NH4 plus. Yeah. So this can be written this way. And in DSC they prefer that you write it this way. Only for this salt do you write the negative ion first. It's just a convention.
Or you have to write the iron.
Yeah,
Iron.
you have to show
like
the charge. Show the charge. Because if you don't show the charge, you are giving other people an impression that this is a covalent compound. I mean, when I write it like this, what do you think? This will make you feel that this is a covalent compound, right? When it is not. This is an ionic salt. This is a salt. How do we know it's a salt? A salt has a positive charge part and a negative charge part, right? That's what we mean by salt. Yeah, so this is why we tend not to write it this way. Yeah, maybe you can write it down now and cross it out for me. Because this gives people an incorrect impression that this is covalent. Yeah, so we don't write it this way, as this gives the wrong impression of a covalent compound when it is not, when it is an ionic salt. Yeah, of a covalent compound. So this, however, is correct because this correctly shows that it is an ionic salt. So correctly shows that it is an ionic salt. Underline the term ionic. Ionic is the true nature of the salt. Covalent is not. Okay? Right, back to here. When RCOOH reacts with ammonia, like we saw, yeah, this is an RCOH. This part is the R. This part is the R. So we can now write this general formula. RCOOH plus NH3 gives RCOO minus NH4 plus. Yeah, so this is the R group. The R. This is the R group, and this will be the R, right? So maybe let's write this in blue. I want it to be consistent. Okay, so you have NH3 here. Yeah, the thing you add, I will show you in blue. Okay, and this is the starting reactant. When RCOOH reacts with NH3, it forms RCOONH4 plus. Can everyone follow up to this point? Yes, and then we heat it. Now you don't have to add anything. You just have to heat it. So heating it would remove water. Where does the water come from? You remove 2 H's from here, and you remove 1 O from there. Okay, so here you minus 1 O. Here you minus 2H. These would then form the water. And let's see what you get. Let's do subtraction now. When I take out 1 O from here and take out 2 H's from here, what is left?
RCO and H2.
Yes. RCONH2. Is it N-substituted or unsubstituted?
Unsubstituted.
Unsubstituted because the N has no L2 group attached to it, right? Yeah, so I know it is like doing math class, right? So, but I still want you to put this. When you do RCOONH4, when you minus OH2, you will have RCO. Just make it look like subtraction because it is subtraction. Okay, so you have this is the water removed. Okay, so this is the water removed. Okay, very intense, right? Yeah, we are getting close to the end. Okay, just bear with me. Getting close to the end of this chapter. We now have to look at the reverse reaction. We just saw how we make ester, how we make amide. Can we undo it? Okay, we can actually undo the process. Okay, we can hydrolyze it. Okay, so let's write this reaction down on the side. Condensation versus hydrolysis. So condensation versus hydrolysis. Yeah, both of these terms, the names are self-explanatory. So condensation is the joining of 2 molecules, removing water in the process. So joining of 2 molecules, okay, with the removal of water. Hydrolysis is the breaking down, okay, you may have heard of a similar term to this, electrolysis, right? Lysis. You learn this also in biology, okay? Lysis means breakdown. Okay, so this is the breaking down of a molecule using water. Okay, using H2O. So one uses H2O, one removes H2O. Okay, so you can say when you remove H2O, is H2O a product or is it a reactant? When you remove something from a reaction, is it a product or a reactant?
Product.
It's a product, right? When you remove something, it will be on the product side. So H2O is a product. When you use something, where do you show the thing you use in a reaction? Is it a reactant or product? It's a reactant, yeah. H2O is a reactant. Okay, so let's take a look at the condensation and the hydrolysis, okay, reaction. Put this numbers. When you have AOH and you have BH, so this is just a general formula. When you go this way, we call this condensation. When you go this way, you remove water in this process. Okay, you will have A, B plus H2O. So this is the water you remove. But when you turn AB back into AOH and HB, you need to put back water. So you need to put in water. This is why H2O is a H2O is a product in this reaction, and it is a reactant in the second reaction. So this is H2O. See? Right? So we are basically forcing H2O back inside this bond, okay, in 2 forms, OH and H. So you can see the OH and H, they are coming from the H2O. We call this reaction hydrolysis. The top reaction, we call it condensation. Right. So we can now hydrolyze, okay, amide and ester by two different reagents. Okay, so can you put down hydrolysis of ester? So still remember the formula of an ester? If alcohols can be represented as ROH, what can you represent ester as? If alcohol is ROH, what is ester? It's RCOO R prime. Right? Oh, put this down. Esters are RCOO R prime. So this is ester. RCOO R prime. We can break it down by using acid or by using base. When you break it down by acid, this is the equation to remember. Okay, it is reversible. You will use acid. And you can see that the H and OH, it goes back to these two ends of the molecule. So let's split it. You have RC double bond O, and then an OR group on the right. Yeah, what about the HOH? Let me write this as, why do I say blue? Okay, if you really want to excuse yourself for the bathroom, you can use that now. But maybe let me finish this sentence at least. You can see that the OH goes here, and the H goes here. So you have the OH and the H. This is where the H2O come from. So you have the OH and H. Okay? Yeah. We have just one more equation, and I'll let you go to the bathroom if you really need that. Okay, you have RCOO R prime. When you react this with OH minus, this is an irreversible reaction. Yeah, and you will have RC double bond O. So you have RC double bond O, and then you have O, and then you will have an H back into here. So you have an H back into here. So this is the OH group. Think of OH group as O minus and H. Yeah, then you will see that the O goes here and the H goes there. Right, so what's the difference in the product? For the first one, an ester will be converted into, what do you call the product? If this is an ester, what is this? Carboxylic acid. Yeah, what about this? An alcohol. Yeah, maybe it's just written in the reverse direction that makes you unable to identify it. But this is actually ROH. You can turn it around and it will look a bit more familiar, right? ROH. Yeah. What about with the second reaction? We have an ester here. We can break an ester down into this thing on the right. We don't call this carboxylic acid anymore. We call this a carboxylate ion. This is an ion because of this negative charge you see here. You can't call this carboxylic acid. Carboxylic acid is neutral. You don't see any charge in here. But this is an ion as it has a negative charge, so we need to add the word ion to address that. Finally, what is this? This is still an alcohol. Yeah. So if the simple equation is too much for you, the least you need to remember is the word equation. Ester plus water forming carboxylic acid and alcohol. Or ester plus hydroxide ion forming carboxylate ion and alcohol. So, yeah, do you need to use the button?
Yes.
Yes, okay.
Right.
And for the other students who may have questions, you can call now. Okay, and maybe ask questions. Also worth mentioning is the fact that this is reversible, but this is irreversible. So if you want a more complete breakdown of the ester, you may want to go with the second method. Because this is reversible, meaning it is an equilibrium mixture. You have 1, 2, 3, 4 substances in the mixture, no matter how hard you try. But for the second method, you can actually push the reaction all the way to the right, so you don't have ester at all. Okay, which means the breakdown is more complete with the second reaction. Okay? Is it too much? Or it's already so much that you're already insensitive to the phase? It's fine. Okay. Maybe write down reversible here first, and irreversible for the bottom reaction. So this is reversible, and this is irreversible. And we'll resume when the other students come back. You may also want to review the earlier reaction because the worksheet that we'll be working on later tests you on everything.
Oh, okay.
Okay? Yeah. Okay, right. I think two students not back yet. We'll give them a minute. So try to review the notes from before first, because the exercise that we'll be working on next tests you on everything. Okay, and I think in the mock we'll also include the.
Okay.
Yeah, I think it will be better for everyone if we also include this in the mock, because the mock should reflect the actual difficulty and the amount of stuff that will be in the DSE. Okay? So we have one more student left. Right. For those of you who have come back, you can try question 1 first on this worksheet. The reactions involved in question 1, we have already discussed it, okay? Yeah, so the question is predicting the intermediates. Intermediates, you can underline the word and then refer it to A and B. Intermediates are things that are formed in a reaction, but they are not the final product. Okay, and yes, you can see here, you have, let me put down, in a reaction, when you have A becoming B, becoming C, becoming D, this is what we mean by the precursor. Precursor means the starting chemical. And there's one final product. Okay. Oh, right. The one that we still have another student left. Okay, so we are referring to the worksheet, question 1. Yeah, question 1 on the worksheet distributed to you last time. So when you have A becoming B, becoming C, becoming D, the final product, of course we just call it the product or final product. The things you get in between A and D, what do we call them? We call these intermediates. Okay, right, so finally everyone is back. So intermediates. So that means the question is asking you to identify the intermediates and the products. Okay, and yeah, we will try this question first, okay, before we resume. The reactions asked by this question is not the one we just discussed, or the ones we haven't described, but it is CH3, CH2, CH2, CH2OH. Well, we can do better than this. we can condense this as C4H9. Okay, so C4H9OH plus, it doesn't tell you what is added to it, but then they are telling you that you have added concentrated sulfuric acid to it, and then you heat it, so you'll get something in here, and then this something will be able to react with chlorine to form yet another thing, and finally this thing reacts with OH minus to form your product. Okay, so this is the final product. So what do you think concentrated sulfuric acid can do? So what can concentrated sulfuric acid do so far? There are how many reactions we have learned involving sulfuric acid so far? I can think of 2 right now. Yeah, what are they? The first one we just saw. Esterification. But we can immediately rule out this possibility. Why? Because esterification requires 2 raw materials. One is the alcohol. We have an alcohol, but this is not the only. Yeah, and then carboxylic acid, so we can rule that out.
Okay.
Rule that out. Okay, so what is that? This is the whole process. Right now, concentrated sulfuric acid is involved in 2 reactions that we have learned so far. So it's used in number 1, esterification. But you remember I said esterification requires 2 parent molecules. You need a parent carboxylic acid and a parent alcohol. And this is where you put the sulfuric acid. And then you have RCOO, R prime, and H2O. But we can immediately reject this because this is the only reactant, right? Do you see it mentioning, there's the use of carboxylic acid? No, we don't see carboxylic acid. So this is not the one we're looking for. So we turn our attention elsewhere. Which reaction of alcohol involves concentrated sulfuric acid? Remember another unusual property of sulfuric acid, it has a strong drive to remove water. So it is a dehydrating agent. So write down the second reaction. Dehydration of alcohol. Now this is the one we are looking at. Do you remember what happens when we have a H and OH group on adjacent carbon? We can add concentrated sulfuric acid. And the concentrated sulfuric acid will help us remove this as H2O. What will be left behind as I remove the H2O from this molecule? What will be left? CC double bond. You get a CC double bond. So you get a CC double bond. So if this is not the answer, well then this one is. Okay, now I'll give you all a task. Help me convert this diagram into something that looks like this. And draw me the alkene. The alkene is this product here. Okay, so what kind of alkene would you get when you dehydrate this starting molecule? So let's do this. We have C. This you can ignore. I mean these CH3, CH2 you can ignore. Or you can draw them out first anyway. So C, 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 C. And then you have OH and H. When you do dehydration on this alcohol, what is the name of the alkene form? When you remove the H2O like you did below, this will become a double bond. What would this alkene be? Bu2 or Bu1? Bu1 in. Remember the number describes where the double bond starts, not where it ends. And we have to count both ways. When counted from the left, it will be carbon number 3 where the double bond starts, but this is not as good as counting from the right. Because from the right, this is the first carbon, and the double bond is here. So this is Bu1 in, write this down. Or I mean draw this out. So the first question mark in here is C, 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 with a double bond in here. Bu1 in. Write everything in lowercase. Yeah, Bu1 in. Which means it's an alkene. Do you all remember the reactions of alkene now? When alkene reacts with a halogen, H2, where would the 2Cl go? Does it insert itself here?
No.
No, but into the C in the double bond, right? So we'll add these 2Cl, we split them, we add them into here. Can you draw the product, okay, form? When I split the Cl and I add it across the double bond, draw the product and name it. Yeah, drawing is easier. So If you don't want to name it first, just draw it. Okay. Oh, you're missing one carbon. Can anyone tell me the name of the product? Dichlorobutane. If you get this, you're so close to the answer. You forgot to tell me where the Cl are in. 1,2-dichloro. So close, so close. So write down Cl. You see what I mean? We split the Cl, we added it across the double bond, and this is what we get. The hydrogens have all been omitted for clarity. The name of this compound is 1,2-dichlorobutane. Right? Don't forget to address the number next time. Okay, you're so close. So this is the second unknown. Now finally, this is a haloalkane, or more appropriately, dihaloalkane. When we add OH group, do you remember what the OH group would do to the Cl? It will it's substitute. Just like when PCl3. Do you remember from just the previous page? PCl3 can substitute the OH for Cl, right? Now we can make the reaction go in reverse. Okay, so you can put this on here. If you want to turn, these two conversions are very common in DSC. When you change our OH into RCl, you need to use the chlorinating agent, PCl3. But when you want to change the RCl back to ROH, you just need OH minus.
Oh.
Yeah, so you just need that. So the OH minus will swap the Cl for OH, and it will kick out the Cl minus in this process. And when you add PCl3 into ROH, it will kick out, what is that acid called?
Hydrochloric acid?
Phosphorus acid.
Phosphorus?
This is phosphoric acid.
I thought it was below one.
Yes?
No. You looked at the wrong one.
Okay. Put down the two equations involved. We just did this earlier, moments ago. So ROH plus PCl3 will give RCl plus H3PO3. And I asked you what number to put here, right? What is the number?
3.
3, yes. Okay. That means you remember this equation we balanced moments ago. So this is the reaction on top. What about the reaction down at the bottom? Well, this is a lot easier, trust me. When you have RCl and you react it with OH minus, the two will just substitute each other. So you can see they are both substitution reaction because the Cl and the OH, they swap places. So can anyone tell me what the products are? And Cl minus. Right, so these two conversions, yeah, it's really like a roundabout, okay, because you can go around and around all day, okay, you can change RCl into ROH and then vice versa, okay, very common conversion. Now do this, apply what you just learned onto this last step, okay, help me predict the product and name it properly this time, properly, okay. When we add OH minus onto this, it will change both Cl into OH. So draw the product and name it. I want to hear about the location of the OH. Don't just say, yeah, don't just tell me about the function. I want to know where they are. So you have 20 seconds, all of you. So draw it. If you answer, at least try. Okay. We are adding OH minus into here. That means we are turning both of the Cl into the OH. Both of the Cl turn into OH. What to name it?
There's an acid involved here. Over here, there's no acid, only alcohol. Okay. It's not used for acid, it's used for alcohol. Yeah. You have to remember the steps for everything. Ester purification.
Yeah, to put it simply, yes. Yeah, you need to remember all the conversions.
No.
But yeah, the more past paper you do, the better.
Okay.
Yeah, the more conversion you do, the better.
Okay.
Yeah, you can't just expect that you look at this notes for 5 minutes and you
This is
remember
what I could
everything.
have
No way.
for. Like
So,
like-
any take on the name?
1,2-butane-diol.
1,2-butane-diol. Very good. Okay. So close. Butane 1,2-diol. Butane 1,2-diol.
Oh,
So
okay.
you have C, 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 OH. Yeah, how to avoid making those mistakes? Let me show you. When you write a number, do you notice something? The number only describes the thing that immediately follows it. When you say 1,2 butane diol, that would break one of those grammar rules in organic chemistry. Because the 1,2, when you say 1,2 butane diol, does it mean that the 1,2 describes the butane? No. No. So to avoid making those mistakes, because I like to think about how we can improve on making certain mistakes. So write down butane 1,2 diol, because the 1,2, what do they describe? They describe the position of the OH group, right? Yeah, as long as you remember this, you will not write 1,2 butane diol. Okay, so yeah, but it's okay at first. Yeah, who doesn't make mistake, right? So this is the product. Pretty intense, right? Yeah, but this type of question, they are pretty common. Okay, in the SE. Of course, it's not like the whole paper is this. The whole paper is this. I will also faint. Okay, yeah, because there will be so many conversions. But before we distract ourselves from the other questions, okay, I want to go back to this thing again. Yeah, we have the what we call acid hydrolysis. So this is acid hydrolysis, as the reactant is an H+. So you need to add H+ for this to work. The second one, we call it alkaline hydrolysis, because we are adding OH- for this reaction to work. So you have alkaline hydrolysis. You know H+ is the representative ion of all acids, and OH- is the representative ions of all alkali. So why do we have a choice here? It seems like we can break ester down by using either acid or using alkaline. But which one is better? Well, depends on what you're asking. If you want the reaction to be more complete, I would say alkaline hydrolysis is better. Can you see that this is irreversible? That means it will go all the way to the right without having any reaction at the end. So if you're thinking about the purity of the product, the completion of the reaction, alkaline hydrolysis is better. But what can acid hydrolysis do better than alkaline hydrolysis is, if you want carboxylic acid as a product, then this will be better, because it gives you a carboxylic acid straight away. But do you get a carboxylic acid here? No. So that's why I said, depending on what question you ask, one of these hydrolysis is better. Okay, so put this down below and write down what is needed. For acid hydrolysis, you will need dilute HCl. Dilute HCl. For alkaline hydrolysis, you will need dilute NaOH, both of which requires heating. Okay, so you will need to heat them to, like you learned in the rate chapter, we heat up reaction, make sure to speed them up. So the heating part is just to speed up the reaction. And put down the question, which is better? The answer is, it depends. Okay, so if the question is, which is better, these two? The answer is, it depends. Depends on what? If you want to get a more complete hydrolysis, so if better means more complete, so if better means more complete a hydrolysis, then alkaline hydrolysis is better because it is irreversible. If better means getting carboxylic acid as the product, so yeah, because this is irreversible. You know, irreversible reactions, they go to completion, while reversible reactions do not. So if better means number 2, getting carboxylic acid as the product, then acid hydrolysis is better because alkaline hydrolysis cannot give you a carboxylic acid. Yeah, so this is one of those, like tricky question where they will give you a context. They will ask you, oh, if I want just more product, okay, I don't care what the products are, I just want it to be more product, then alkaline hydrolysis. If the question wants you to make carboxylic acid, oh, I want you to make carboxylic acid, then this is better. You see what I'm saying?
Yep.
Okay, so let me finish this sentence first. Acid hydrolysis is better because our COOH is a product. Okay. Right. Just bear with me. One last reaction, I promise, and then we'll mark the end.
How
of
many
this.
more?
One last reaction, which is also acid and alkaline hydrolysis, but not of Ester anymore, but of amide. Okay, but don't worry, they work in very similar way. Let me assure you. I will copy this on the next page, and for you to compare, so you can see how similar they are. So let me copy this first, and I'll paste this in here. This is the hydrolysis of Ester we just saw. Now we will apply the same concept onto the hydrolysis of amide. Yeah. So remember amide, and I like to think of them as distant relatives. Okay, amide and ester. Esters, they are RCOO alkyne. I will look for the COO, the COO, COO. When I search for ester, yeah, COO. Okay. When I want to search for amide, the distant relative of ester, I look for con. So I look for con. Okay? So as there is a CON group in here. So that's the difference between amide and ester. To me, they are distant relatives. They look similar. And not only do they look similar, the reactions are also similar. So to show you how similar they are, I will just copy these two parts in here. Because the same reaction applies to them. Acid hydrolysis and alkaline hydrolysis. So we'll copy them over again. Yeah, but for you, unfortunately, you have to write down. Okay, you cannot copy it. So you have RCONH out or NH2. Yeah, or RCONH out or RCON out 2. So this is to show you that the H's, they can be unsubstituted, or they can be substituted with one alkyl group, or they can be substituted with two alkyl groups. Doesn't matter, they are all amide. They are all living under the same roof. The roof being amide. Okay, they are all amide. Okay, there's not a difference in here. When you do acid hydrolysis onto them, okay, what will happen? Same thing. You have RCONH2. When you do acid hydrolysis, the reactant is H2O. And the reaction, okay, interestingly, hydrolysis of amide is always irreversible. But hydrolysis of ester, depending on whether you use acid or alkaline, one is reversible, one is irreversible. But here both are irreversible. If you will put down these two arrows first. They are both irreversible here. Okay? Like that. And the rest is really identical, okay, to what we saw. Maybe you can predict the product. Can you do the same thing we did earlier? If we treat H2O as HOH, and we add the HOH across this the CON bond, can you tell me what will we get as the product? So if we force the OH back into the CO double bond, and we force the H back into NH2, what do we get? We get
acid?
a carboxylic acid and
water.
And
No acid.
yeah, this is a carboxylic acid. Yeah, this is where the OH. Ammonia, yes, very good. Ammonia, so you get the H back. Yeah, this is why I said you don't have to remember this as two different concepts. Yeah, buy one get one free. If you remember this, you remember also this. It's really the same reaction, don't you think? It's really OH and H. You also split OH and H back into here. But because of the difference in the composition of amide and ester, the products are differently named. This is a carboxylic acid still, but like you mentioned, this is ammonia. You get carboxylic acid and ammonia here. Okay? Right. Now, I will let you guess what alkaline hydrolysis would give. It's really identical. Okay? Just look. Okay, they're the same. These two are the same. Okay? Can you predict what will happen when I do alkaline hydrolysis on RCONH2? I'll give you 20 seconds. Draw me the product. Draw me the product. If you don't know what to do, you can borrow a few pages from this reaction. It's quite similar. 20 seconds. Look at this reaction and find some pattern. Apply that pattern onto here and predict the product. Yeah, think of OH as O minus and an H. You will put the O minus here to the CO double bond, and you put the H there. Okay, but by there, here it will be OR prime, here it will be NH2. Yeah, 20 seconds to figure out the product. Drawing is easier than thinking what it looks like. Don't think about things in your head. You have to draw it out. So close, so close. So you do it like OH. This is going to be O times here. Yes, so that is it. Okay, right, I see that some of you have got the answer, okay, so, and that is, write down OH minus first. You can split OH minus into O minus and H.
Oh.
Yeah, and then you add the O minus to the RCO double bond. Yeah, which means you get a what do you call RCO?
Carboxylate ion.
Carboxylate ion, yes. Okay, so you have RCOO minus, and you get ammonia. Okay, but there is a tricky part in here. Is that they will tell you in the end, for acid hydrolysis, you will not really get ammonia. Why? You will get ammonium ion instead. Why? Does anyone know why? For acid hydrolysis, ammonia will actually not form. That's because, what is the acid-base nature of ammonia? Is it acidic or is it basic?
Basic.
Basic. It will react with the acid to form NH4+. Yeah, so this is to show you that what you learned earlier, they will still be appearing later.
So regret.
Yeah, so but put down the name first. This is carboxylate ion. So carboxylate ion and ammonia. Yeah, but the first reaction will not really form ammonia. Why is that? For acid hydrolysis, put two stars here. Okay, so for acid hydrolysis of amide, yeah, okay, ammonium ion will form instead of ammonia. Ammonium is NH4+, will form instead of ammonia because ammonia, you remember from acid and base chapter a long time ago, is basic. It will react with H+, which is what you're using in acid hydrolysis, okay? Yeah, the acid from acid hydrolysis to form NH4+. This is why you will really not get ammonia. You will get ammonium instead, okay? Because there will be so much acid around that as soon as the ammonia gets formed, it will react with the H+ to form NH4+. Okay? So to sum it up, yeah, I know this is I promised the last reaction, okay? But together with all the reactions you learn, that adds up, okay? And we will try some of these questions now, okay? Yeah, don't worry, I don't read students the answer. We will try the questions together. But of course, we will not be able to finish them all. So some I wanted to do as homework, okay? But first, let's do a very quick summary first. When you have RCOO prime, when you do acid hydrolysis, okay, the reaction will form RCOOH and R prime OH. When you do alkaline hydrolysis, this is irreversible. You get carboxylate ion and R prime OH, the alcohol. With amide, RCONH2, when you react it with H2O and H+, like I said earlier, both hydrolysis of amide is irreversible. But for ester, one is reversible, one is irreversible. Yeah, that I think might be important to point out here. So you have RCOOH and you have NH4+. So the NH4+ results because of what we mentioned. Ammonium will form instead of ammonia. And then when you do alkaline hydrolysis, you will have RCOO- and NH3. Yeah, so you see the products are very similar. Do you see? When we hydrolyze ester and amide by acid, the products, one of the products will be carboxylic acid, right? And when we hydrolyze ester and amide with alkali. One of the product is carboxylate. So this is why I think by this point, both of everyone here will agree that they are very similar. They're very similar. Well, the reversibility of the reaction is not similar. Yes, there I mean, but the products are very similar. Okay? Right. So now, time to, do some questions together. Okay? So, but first, we'll do a quick review first to let you see that all the reactions that we've learned so far, they're connected. Yeah, unfortunately, okay. So we have the organic summary. And this would be part of your mock exam as well.
This is the end of chapter, right?
Yes. Actually, the next chapter, I think chapter 45, is actually just a reiteration of chapter 44. Okay, but they are showing you the entire pathway. And I'll do this with you now. Okay, I won't just ask you to read. Okay, don't worry. So we have organic summary. We have learned how many compounds so far and their reactions. We have learned alkane, alkene, alcohol,
Carboxylic
carboxylic acid,
ketone,
amide, ketone,
ester,
ester, aldehyde. I lost count of how many. Okay, so which is why now.
Nine.
Yeah, let's tie them all together. So we have alkane here. There are two approaches for students. If I were you right now, when I'm just a beginner to organic chem, I will first write out all the reactions associated with each compound. Yeah, we'll look at them individually first, and then we'll try to tie them all together. Okay, which is what we'll do now. For alkane, how many reactions do you remember?
No.
No. Well, there's at least one. Trust me. Combustion.
Oh.
You must at least remember combustion, right? Yeah, so combustion. Write down number one. Alkane can react by combustion with oxygen. Combustion means reaction with oxygen to form what?
What?
CO2 and H2O. That's one. Okay, yeah, that's one. CO2 and H2O. Because alkanes, they are hydrocarbon. Yeah, don't forget, alkanes are hydrocarbon, meaning they can only have C and H. And so the products must contain C and H. And because this is the reaction with oxygen, you get oxides. Okay, the first reaction. Are there any other reaction you can think of?
No.
No. Substitution. I hate the word substitution. So you react with halogen, yeah, or like bromine or chlorine in the presence of UV light. Yeah, sunlight. Yeah, UV light is better than sunlight because sunlight, one part of sunlight is UV light. There's also visible light. Yeah, but it's okay. If you write sunlight, it's okay. You have write down the condition. You need UV. Yeah, and then you will form a mixture of haloalkanes, which are OX, and hydrogen halide, which is HX. Yeah, I will use one example, and I can guarantee you that you know what I mean by this. Okay, let's take this example, CH4. CH4 is an alkane. When I react CH4 with Cl2, okay, how many products can I get? Well, let's see. Look at CH4. CH4 has 4 CH bonds. To me, I like to look at it this way. What is substitution? Substitution always means something going in, something coming out, right? Yeah. So that means you can use this concept, and then you will be able to figure out what product I assure you. Can anyone tell me what is the first product I can get from swapping one H with one C? CH3Cl. What is the name? The name of this product. You need to think. The more you use it, the more you
Chloromethane.
Chloromethane. Excellent. Chloromethane. Can you put down CH3Cl? But you know, you heard what I just said, right? When something goes in, something goes out. When this H comes out and bonds with Cl, what do you call it?
Hydrogen chloride.
Oh, it is hydrogen chloride. Hydrochloric acid can only be formed when there's water. There's no water in here. Okay, so this is hydrogen chloride. Can you write down HCl gas? So in this process, you will get HCl. So an HCl molecules like creep out of the reaction mixture like that as a gas. Let's continue. We will then substitute it the second time. We have, you know, the molecule is not like completely rid of CH bond yet. Okay, so we still have 3 CH bonds remaining. So let's keep on substituting it. What's the next product?
CH3CO2 or CH2CO2. CH2CO2.
CH2CO2. Can anyone name it? See if you name it correctly.
Dichloromethane.
Dichloromethane, yes. No need for numbering because there's simply nowhere else. I mean, there's no other carbon you can attach to CO2. There's only one carbon. There's no confusion. So, write down chloromethane, dichloromethane. So I'll speed up the process. We have dichloromethane. What is the next one? When you have 3. Trichloromethane, and finally you won't stop until you get tetra. So put that di. Quad is not the prefix we use in chemistry. So we have tetra. But yeah, quad means 4, but not in the context of chemistry. Okay. So just write them down. This is CH3Cl. This is CH2Cl2. You can use the pattern here. When you remove one H, you give it back as Cl. So that way you will not make mistakes. Okay? The next one is CHCl3. And finally the reaction comes to a stop when all the H's are gone. You can think of it as like the Cl won't give up until we finish converting all H's into Cl. It won't stop. Okay? It won't stop. And that's the halo alkane. What about hydrogen halide? You can see this hydrogen halide in here, right? This is the hydrogen halide. And these are the alkynes. This is why I said a mixture will be formed. You don't just get one product. You get a mixture, a cocktail of product. Which is why this is not a very good way to prepare halo alkane. Imagine this. If I want you to just prepare this, but then you end up giving me, oh, here's this and this and this and this and this. Will you like the other products when I ask you to just prepare this product? No, right? It's like when I ask you for just pasta, and then you made a few dishes, not just pasta. Oh, here's rice, risotto, and then fruit punch. But I didn't ask for those. I only asked you for pasta, and you're giving me the other things. So this is not very helpful, you see, for preparing a certain halo alkane. So that's the second reaction. We have the third reaction. Does anyone remember? Cracking. Cracking. What is the catalyst for cracking? There are 2 catalysts possible for cracking. Silicon dioxide or aluminum oxide. Put that down. That's the third reaction. Yeah, cracking. You learned this in Form 5. This last year. Okay, so there's no oxygen. You have to make sure that there's no oxygen around and that there's the catalyst, Al2O3 or SiO2. And what can you crack alkane into?
Smaller
alkane and alkenes. Okay, so smaller alkane plus smaller alkene bracket S. Okay, alkene bracket S. Why? Okay, why is there a bracket S in here? Let me give you an example. What is the formula of an alkene with 10 carbon? I want to check if you remember the general formula really.
C10H22.
H22. Excellent. So you have C10H22. Now I want you to think of a number between 1 and 10. Any number will do.
5.
5. Okay, well, I will use both. Okay, so if you have an alkene with 2 carbon, what would be the alkene like? So, you know 10 carbon can be split into 2 halves. 1 half with 2 carbon, the other half with
8.
8. Okay, 8.
5.
And for the other example, you can also split it into 2 fragments. One with 5 carbon, the other with 5. In fact, we can do this all day. Yeah, you can use 3 and 7, 4 and 6. Any number will do. Okay, so let's just put one more. Can you tell me what's the formula of an alkane with 2 carbons?
C2H6.
C2H6. What about an alkene with 8 carbons?
C5H10.
C8
C5H10. 8 with 8.
alkene.
C5H10.
C8, this is 8. So
Oh, it's
C8,
8. Okay.
8, 16. Right? Yeah, so you have an alkane here and an alkene here. Right, so, and can anyone tell me the answer to the second one?
C5H12.
And,
C5H10.
yes, the last one.
10. 10.
12. Very good. But you notice what I wrote, right? Alkene, bracket S. That means we can also have another variation here that produces C4H10. And can you think of 2 numbers whose sum is 6?
3.
3 and 3, maybe,
Yeah.
or maybe 2 and 4. What is an alkene with two carbon and 3 carbon and 4 carbon? And yeah, you see the number adds up. 10 plus 4 plus 8 is 22. 10 plus 12 is 22. 12 plus 10 is of course still 22. 22. It's just math, okay, in a nutshell.
I hate math.
That's alkanes. So you see you can have one alkane or one or more alkenes. What is the test for alkene?
What was it? Changing color. Something changing color.
Bromine water.
Oh yeah.
Yeah, bromine water. So to test if you have successfully produced alkene from the cracking reaction, you can test it for the CC double bond. So we have, let me put this down. This is supposed to be a quick summary. Okay, so alkene, the test for CC double bond. We can use number 1, bromine water. What is the color change when you use bromine water?
From brown to colorless.
Brown to colorless or orange to colorless. That's because when you have CC double bond,
Bromine.
the bromine, yes, will add itself into the double bond, forming a colorless product. So you'll have CC. So this is why I'm writing it in black, because it now loses its color. It was orange or brown in color, but then it becomes colorless at the end. So the color change is from orange to colorless. And then, yeah, this is the test for bromine water. The test for C double bond, we call it bromine water test. Now that's for just alkane. What about alkene? What are some reactions of alkenes? I need at least 2 from you.
Halogenation.
Halogenation,
Wow. Addition.
hydrohalogenation,
Addition polymerization.
addition polymerization, yes. Okay, so I'll write down the rest for you, okay? There's no other way than to remember. If you ask me how do I remember, well, I just remember it. What? There's no other way. Yeah, no other way around it, I'm sorry, okay? Yeah, but now okay. So you have reaction with hydrogen. The catalyst is platinum, okay? So platinum metal, very expensive metal. And then we have halogenation, no catalyst is needed. We have hydrohalogenation, so HX. And then we have, what else? Okay, we have addition polymerization. So addition polymerization. Right. Yeah, and these are the most important reactions. Let's write out the product. When alkene reacts with hydrogen, they will be turned effectively into alkane, into just alkane when you add hydrogen to them. When you add H2 into CC double bond, you get dihaloalkane. Yeah, dihalo. I need to stress that it is dihalo because there are 2 X's, okay, added. And this is just a monohalo, or let's just drop the word halo, haloalkane. And addition polymerization will form polyalkene. Polyalkene. What is the test result? The bromine water test result on polyalkene?
Stage 1.
Very good. Okay, so you can
Yeah,
see
because
what the
polyalkene
trick
is
question
an
is.
alkane.
You see, I'm trying to trick you into saying that, oh, this is an alkene. So it will turn bromine water from orange to color. Why doesn't it turn bromine water from orange to colorless?
Doesn't have a double bond.
Yeah, don't get fooled by that. I know what I'm writing. This is polyalkene. But polyalkene is an alkane. Okay? Yeah, so if you don't see what the problem is, write this down. This is alkene with a CC double bond. Yeah, okay, I'm very happy. Okay,
Only
so
one
we get
person
the
writes.
answer. Yeah, well, I
Okay,
think there are some other students who also know the answer. They are just too, shy
We'll
to
try.
tell me the answer.
Try, man.
Okay, and don't need to be shy. We have so many lessons already together. Yeah, so.
So you don't know our names yet?
You still don't know what
I
it is.
will,
You
okay.
don't even
I will-
introduce yourself for the first lesson.
I will, yeah, it's still taking me a while to identify all the students. I will print out a paper and I'll look at it more. So excuse me, for, right. So you have poly, okay. So this is actually an alkane, okay? So it will return you with a negative result with bromine water. Okay, it will return you with a negative result. So you can put this on. This turns, this one turns bromine water from orange to colorless. Yeah, from orange to colorless. Yeah, that's true for alkene. But for the product polyalkene, bromine water stays orange. Yeah, despite the name, because it is really an alkane. Despite the name, is that clear? So that's alkene, okay? And then we have, what are the other reactions? With alcohol, okay? So alcohol is even more interesting. We can tie alcohol to haloalkane. Now I'll ask you something I just told you moments ago. How do I convert alcohol into haloalkane? What do I add? PCl3. Or if the question changes and they want you to make bromoalkane, then we use PBr3. If it wants you to make iodoalkane, PI3. Yeah, it's always PX3 in other words. Okay, write this down. So for alcohol, you can turn them into haloalkane by using PX3. X is equal to Cl or Br or I, depending on the question really. So you will get RX. Okay, if you use PCl3, you get RCl. PBr3, RBr. That's it. So this is haloalkane. What else? We learn to classify primary, secondary, and tertiary alcohol. Which of these three classes of alcohol can be oxidized?
First two.
First two, or meaning primary and secondary. Tertiary, can they be oxidized?
No.
No, yes. So therefore we will have to split them off into three different groups because we have to treat them differently now. So primary, secondary, and tertiary, make sure you still remember how to identify an alcohol by the number of alkyl groups on the side. Primary has 0 or 1 alkyl group. Yeah, I repeat, having 0 alkyl group is also a primary alcohol. Because a lot of students, when they look at the question and they read H in here, and then they are immediately confused. Because they remember that, oh, primary means 1 alkyl group, right? What about those with 0 alkyl group? Are they primary? They are still primary alcohol. So can you put down this note in here? Primary means 0 or 1 alkyl group. Methanol, for example, has 0 alkyl group, but yet it is a primary alcohol. So you have 1 alkyl group, 2 alkyl group, so 2 alkyl groups, and then we have 3 alkyl groups. But you have al. The third one is very easy because there's no reaction. Okay, so it cannot be oxidized. Okay, so no oxidation. But can anyone tell me what primary and secondary alcohol can be oxidized to, and how many stages of oxidation can primary alcohol undergo? 2 stages. First into aldehyde, later into carboxylic acid. What about secondary?
Ketone.
Only ketone. Okay? And now, to add to that, put down also the conditions Okay, so we have
There's
Al,
conditions.
yeah, which one is distillation, which one is reflux? I let you tell me. So this will first form LCHO and LCOH, and this will form LCOL prime. Yeah, so which of these reactions you can tell me now requires distillation, which requires reflux. So for the first arrow on the top first, this one, distillation. Why would distillation work here when reflux will not give you aldehyde? Because which of these has a higher boiling point?
Alcohol.
Alcohol. Why would this have a lower boiling point?
No.
Because it
No
lacks
H bond.
H bond, lacks H bond. Very good. So lacks H bond. So can you put down this as distillation? So you see, you actually remember it. It's just that now that we are doing a summary, it's coming back here. So doing the summary yourself is very important. Okay, it will be even better than if I do it with you. Okay, this summary. And then on the side we have reflux. Yeah, remember reflux is a way to push the reaction to the very end. Okay, push it to the terminal. This is the terminal. Remember, I compare this to a MTR rail. You want to push the reaction all the way to the end, then you use reflux. Whenever you want to go all the way to the end, you do reflux. Okay? And the oxidizing agent, what is the name of the oxidizing agent? Potassium dichromate. But still, you're missing one word. It's acidified potassium dichromate. Okay? So, yeah, write this down. Oxidizing agent must be double line the word acidified. I already reminded you the importance of acidifying. If you don't acidify it, it is a useless oxidizing agent. So acidified potassium dichromate. What is the formula?
ACR07.
O7. Don't forget /H plus. So this is the acidified part. What is the color change if there is an oxidation? It will change from orange to green. Yeah, if there is no oxidation, it will remain orange. Yes, so put this down. These are where there is an oxidation. This is where there is no oxidation. So if you do this, if this is a tertiary alcohol, adding oxidizing agent into it would not result in a color change. It will just remain orange. So no change in the color. Oh, wrong man, sorry. So no change in the color, it will remain orange. But when you have oxidation going on, whether it is to aldehyde or carboxylic acid or ketone, if there is an oxidation, you will see it changing color from orange to green. Can you tell me what is the formula of that green chemical? Cl3 plus. Cl3 plus. Yeah, so you will have, you see, Cl2O7 2 minus cannot become Cl3 plus in here. This is why it remains orange, as it cannot go forward. The dichromic ion cannot become chromium because there is no oxidation. And in here, this is primary or secondary alcohol. When you add the oxidizing agent into it, now the oxidizing agent can go forward and become Cl3 plus. Okay? That's alcohol. And anything unclear about this reaction? No. Okay, now we look at, so this is the, like a forward reaction. The backward reaction, we call it reduction. Okay, so we have LCHO, the aldehyde, and the ketone. Okay, so we have aldehyde and we have ketone. Aldehyde is more special because it can react either by oxidation or by reduction. Okay, I like to think of oxidation as like a process of raising the oxidation number, and reduction as a way of reducing the oxidation number. What can aldehyde be oxidized to, and what can it be reduced to?
Oxidized to carboxylic acid.
Carboxylic acid, but aldehyde can be reduced to which class of alcohol?
The first class of alcohol.
The first class, meaning the primary alcohol. Yeah, so you can say it can move up into carboxylic acid, and it can move down to primary alcohol. So it can move down to primary alcohol. But not so fortunate for ketones though. Ketones, can they move up or can they only move down?
Move down.
Move down, why? Because, do you remember the MTL map? Is there anything beyond the ketone point?
No.
No, it cannot move further anymore. It can only move back. Into which class of alcohol? Secondary, okay? Yeah, so it can go down. And can you write down 2 examples of a reducing agent? Do you remember the 2 reducing agents? I said one is especially dangerous. One, if you use it with water, it will explode. What is that very powerful reducing agent?
Lithium. C.
You can write the formula. You don't have to tell me the
Li something.
ALIALH4.
4.
How do you remember it?
How?
We don't.
We
We don't.
Well, you do. Some of you do. Some of you do. Okay, yeah. And this is why you need more practice. So you have secondary alcohol. And practice makes perfect. Okay, so you have 2 possible reducing agents. One is LiAlH4. The first step is to use this with dry ether. The second step is to add H+. So when you do this, you will turn a ketone or aldehyde into secondary alcohol or primary alcohol. Yeah, this is when you use the reducing agent LiAlH4. But this is a very unusual reducing agent because when you use it with water, it will explode. This is why we emphasize dry ether. Yeah, dry ether is to ensure that there's no water that will react with. So no H2O can react with LiAlH4, which will lead to an explosion. The second alternative would be to use NaBH4. Yeah, let me tell you how I remember this. Do you see that on the periodic table? You can use the periodic table to kind of cheat. Okay, why? Do you see where Li and Na belong? Li is here, Na is here.
Yeah.
Do you see where Al and B belong? B is here, Al is here.
Yeah.
So that means LiAlH4 is really NaBH4. It transformed into a different group member, you see. Yeah, you can check.
Oh.
B and Al are in the same group.
Yeah.
Li and Na are in the same group. So this is why LiAlH4 is really NaBH4.
Cool, can you move?
Oh,
Right.
yeah, that makes sense. Okay.
Yeah, makes
No,
sense.
no, it's
yeah.
not.
So
It's
I'm trying to make sense, okay, of this for you, so you can remember it.
Dry what?
Yeah, if you know all these tiny little things, it will make it easier to
Yeah,
remember.
later.
Yeah, so can you put down?
Like,
For this one, you
organic
can use
substance.
water.
Dissolve stuff.
Yeah,
If you can't use it in water.
yeah, so you can use
So no,
aqueous.
no water, because then it's
And then, yeah, you will turn aldehyde and ketone back into secondary and primary alcohol. So this is reducing agent. And the only thing I need you to remember is that one of these reducing agents are very difficult to work with. You have to use dry ether. The other one, NaCH4, can be used with water. So LiAlH4 cannot be used with water. But NaBH4 is milder, can be used with water. Yeah, so always look at the periodic table. I try to cram everything into the periodic table so I can remember less, and so should you.
Oh,
Yeah.
okay.
Okay? So that's aldehyde and ketone. And make sure you write this down. That's a tiny difference between these. Okay? One would be to use LiAlH4 and dry ether, and then this is step 2. Yeah, so you have 2 steps when you use LiAlH4. When you use NaBH4, there's only 1 step required. Okay, the only step. Okay, so only 1 step required. And it will get you to the same destination, okay, which is secondary or primary alcohol, and from the same starting point. Okay, it's just a matter of choice. Yeah, depending on whether they are giving you water as a solvent or an organic solvent as a solvent. If you have an organic solvent, that means there's no water. You can use LaOH4. If they are giving you water, they are telling you that, oh, I have an aldehyde aqueous solution. Don't even think about using LaOH4 in that case. It will explode with water. Okay? Yeah. And then what? Okay, I think that's pretty much it. Okay, except the Ester and the Amide thing we just discussed. Because we just discussed it, I will not put it on the summary, or else it will take the whole time. I would like to work on one more question with you. Maybe two, okay, if time allows. We have question 2. Okay, question 2. What do we mean by synthetic route? Okay, so for, yeah, you can go to the worksheet, okay. Question 2. Suggest a synthetic route for the conversion of 1-chloropropane to 1,2-dichloropropane. I want to draw them out first. I'll give you all 30 seconds. To draw out the reactant, you see I gave you two, I give you a large blank space here and wrote reactant and product. Draw me the reactant and product. Take the structure of your own liking, whether skeletal formula, whether condensed structure or full structure. I will suggest that you draw skeletal formula. Okay? Yeah, we'll check the answer in skeletal. Yeah, skeletal formula. Okay. And then, what do we need to learn in chapter 45? Which is what I made this, why I made this exercise, is you need to know something called retrosynthesis. So you know when you go retro, you use things from the past, okay? So retrosynthesis means you look at, once you're done writing down the structure, you can look up and we can write down something else first. When you are asked to convert a reactant and product, what we do is to use the concept of retrosynthesis. We'll first think about all the possible things that the reactants can give. And we will think about all the things that can lead to the product. So think about all things that reactants can give. Yeah, so find out all things reactants can give. And then number 2, find out all things that can lead to the product, and you try to find a connection. Okay, there will be something that is identical. So let's just say you have A, B, and X, and then you have X, Y, and Z. You will be able to find a connection. You tie them together. This is what we mean by retrosynthesis. We try to identify a path from reactant to product. So can you put down the second point? We want to find out everything that can form the product. So find out all things that can lead to the product. Yeah, maybe I will use this as an example, and then we will do another one. You will do another one yourself. Okay, so this is point number 3. Point number 3 is to find a connection. Okay, find a common. Do you remember what you call things that are formed in the middle of a reaction, but they are not product? Intermediate. Intermediate, very good. So put down, find a common intermediate. So intermediate. Yeah, so in this reaction, you have reactant becoming X becoming product. Okay, so you can write down that's the intermediate. So you have reactant becomes X. Yeah, so this is the intermediate. Find a common intermediate, and that's what you do. Let's use this example, okay, to illustrate. And for everyone who have who have drawn the structure, check your answer. 1-chloropropane should look like this. Okay? And 1,2-dichloropropane. Oh, and I know some students will disagree when they draw this, especially when they're starting stroke points down. It doesn't matter, as long as there are 3 carbons and the Cl is good. Doesn't matter the starting stroke. It doesn't always have to point up. You can point down. Okay? Right. So this is 1,chloropropane. And then we have what? we have the product 1,2-dichloropropane, which looks like this. So 1,2-dichloropropane. So just like before, your starting stroke can also point down. It really doesn't matter. So you can have this. Yeah, doesn't matter. Yeah, you can also move this up like that.
The same.
Yeah, the same thing. Okay, nobody will judge as long as you have the correct number of carbon. So I'll just stick with one. I don't want it to look very messy. Okay, this page. So we have 1,2-dichloropropane. Let's do what I asked you to do just now. What did I say? You find out everything that the reactant can form. Can you identify this reactant? Which class of compound does it belong to? Is it alkane, alkene, alcohol, haloalkane, carboxylic acid, haloalkane, right? Go through your mental drawer. What are the things that haloalkane can react to get? Remember that conversion between
With more halogen gas to form.
haloalkane can be converted back to alcohol. How?
Wait, no. Alcohol?
How do you convert haloalkane back to alcohol? Remember that conversion? How do you convert haloalkane back to alcohol?
PCl3.
Haloalkane back to alcohol. Hydroxide. Okay, so that means you really have not many options here, you see. But can you draw this? This is a haloalkane. Yeah, I know a lot of students find this unnecessary, but let me tell you, this is the most important step of all. Because if you don't know which class of compound this belongs to, you don't know what it can become, right? Yeah. So, and in fact, if you go through your mental draw, there's only one reaction that halogen and alkane can react to give, and that is alcohol. Okay? Yeah, which means this is our only lead. Okay, so can you tell me what can alcohol become? Yeah, what can an alcohol become?
Carboxylic acid.
Yeah, alcohol can become carboxylic acid. What else?
Aldehyde.
Aldehyde. What else?
Ketone.
Yeah, ketone, yes. So we have ketone, aldehyde, carboxylic acid. There's one more thing. Remember what happens when I add concentrated sulfuric acid into it?
Dehydration.
Dehydration of alcohol will form
Alkene.
alkene, yeah. And this is an alkene. Right. Before I tell you which one is the intermediate, I'll let you decide. Let's look at the product side now. You see, you have used up all the leads for the reactant. Yeah. If you keep on going, of course, you will leave you somewhere. But I think it's also good that we look back from the product. Can you identify this product again?
It's an alkene.
This is a haloalkane.
Oh, right. Hello.
Yeah, so this is also a haloalkane. Now my question is, what can become a haloalkane? Be careful. The question is, what can become a haloalkane, not what haloalkane can become. What can become a haloalkane?
Alkene.
Alkene, yes. So can you see that? Can you see that there is a lead now? You can go from alkene to haloalkane. That means this is the intermediate you need to identify. You don't want to join them together, see, like on the left. You know, reactant can form 3 compounds, A, B, and X. And you know, product can be formed from 3 different compounds, X, Y, and Z. Do you see that there is an X involved in both cases? This is what I mean by the link. You link them together. So that means the reactant can react through X into the product. This is the only way possible, right? So let's start. Can you tell me what will happen to this haloalkane when I add hydroxide ion to it?
The chlorine is replaced.
So the chlorine is replaced with
Hydroxide.
hydroxyl. Okay, you know you add hydroxide ion, yes, but then the group will be turned into a hydroxyl group. So I want you to name this. This is 1-chloropropane. We already know it. What is the name of this compound? What is the name of this compound?
Alcohol. Propanol.
Propane 1 mole.
Propane 1 is better.
Okay.
Propane 1 is better. Okay, so 1 chloropropane. Does anyone know why it should be called propane 1 instead of propanol? Because the OH group might as well be put on position 2. If you don't state, that means it is possible. Okay, so you will have to state out the name to indicate that, well, yes, it is indeed attached to position 1, not to position 2. We always want to avoid confusion in organic chem. Okay, add a number if you think it will cause confusion. Next up, what did we say is the lead? Alkene. What can we add to turn an alcohol into alkene?
PX3.
Yeah, sorry? No. It's corn sulfuric acid, right? What is the alternative dehydrating agent? See if anyone remember. It's Al2.
Oh, three.
Oh, three. Okay, like it's almost like you're squeezing out one letter at a time. So yeah, concentrated sulfuric acid or aluminum oxide. Yeah. Okay, I know how many pages ago. 1, 2, 3, 4. I lost count. Almost 10 pages ago. If you still remember it, thumbs up. Okay. So you have Al2O3 or corn sulfuric acid. Yeah, put down the nature of the reaction so you can understand it better. This is substitution. Because the Cl and the OH they swap. This is called dehydration. Because water is eliminated. Okay, I will give you some time to draw the product when I dehydrate. Dehydrate is alcohol for me. Remember, dehydrate means to remove H and OH. So you have a C here. Right. Yeah, remember when you do dehydration, you don't do it randomly. You have to find an H and OH on adjacent carbon. You can't remove the H and OH from the same carbon. That's the last thing you want to do. You want to remove H and OH on adjacent carbon. This is what we mean by adjacent carbon. They have to neighbor one another. This will then be turned into what? Into alkene. I want you all to draw the alkene and name it for me. Yeah, before we end this, okay?
Propene.
Propene, yes, propene. Like that. So now where do we go from here? How do we turn propene into 1,2-dichloropropane?
CO3.
We add
3CO3.
no, you add PCl3 only when you want to change OH group into Cl. This is not an OH group, this is a CC double bond. With CC double bond, it's a lot easier. You just need to add Cl2. Because Cl2 means you are adding the Cl across the double bond. Yeah. Right? Yeah. I kind of like this chapter because if you
No,
can solve it.
why do you like
Why
this?
do you?
Protest. It's your case is really weird.
Yeah, I'll pay you back. Okay. Yeah, because, okay. But don't you think if you can solve the problem, it's very rewarding?
Yeah, but what
Yeah,
cause?
it's solving a puzzle. Okay. Let me finish putting out the name and we'll end the class today. This is propene, and this is 1,2-dichloropropane. So I want you all to challenge yourself to finish.
No, thank you. No, thank you.
Please.
Thank you. Next.
Yeah. So at least finish half of the question.
No!
Half.
I will upload the answer to you, but sometimes I want you to try. If I just show you the answer, what's the point? Okay, yeah, you have to try, please. Okay? Yeah, and then we will move on to the next part. We have just one chapter to wrap up in organic chem before we can move on to the patterns in chemical world and then later to electrics.
We still have more to learn. Oh my god.
Yeah, I think
We have
20 some chapters left.
We have 6 room peppers.
Yeah, wait.
Yeah.
If you have questions, you can.
Oh my god. Okay. What's next?